Um, okay, well, I'll give the introduction in English since this video will go taped and then go onto YouTube later. So if you have any colleagues or friends who would like to see classes, they will be available on YouTube and the Miro channel. So today we have the pleasure of having Professor Lucas Céleri here to give us two classes, one today and one on Thursday, about information theory, foundations, and applications. Lucas is a professor at the Institute of Physics at the Federal University of Goias, where they have lots of piqui. So piqui is a fruit that is in lots of the food. If you visit Goiás, you can have piqui. So he's leader of the quantum piqui group, and some of you have received, I forward you different talks that they sponsor online and so on, so some of you have attended those. So okay, please join me in welcoming Lucas here, and thank you very much.
Okay, good afternoon. Thank you very much for the introduction, for everyone for being here, and for inviting me actually to come back here in Chile, in Concepción. So as Chile just told you, I'm working in this university here. The logo is this guy here, and this is my research group that you have to. First of all, things that we always do is analyzing funding agencies, and I just forgot two of them here, but I'm sorry for this. Of course, Universidad de Concepción, that I think here, and this is a network in Brazil that is dedicated to studying quantum information. It's 20 years old now, this network. And there are too many colleagues and friends that taught me information theory along these years to be listed here, a bunch of them. So, how's going to be this thing? Steve asked me to talk about quantum information in general, but this is a course of quantum information, so I decided to talk about classical information. And why? Because usually in quantum information courses, we don't have these things here. And why are those? Those are the two theorems that rest on the basis of all information theory, classical and quantum. So they are known today as Shannon coding theorems, and we're going to prove these guys. Not prove exactly proof, because the proof is quite complicated, but to give a bird's eye view on this thing. And then in the second class, we will apply these things. Apply information theory to classical thermodynamics, and apply information theory to quantum phase transitions, quantum information theory, and apply quantum information to thermodynamics and definite causal order, or a different thing that I didn't decide yet. I will decide to touch it. Unfortunately, it's not possible to talk about any more things that are very nice, but if anyone of you wants to talk to me, just knock on my door. Which office?
Carlos Saavedra's office.
So, all of you know I'm there until next week, so you can feel free to knock on the door. So let us start with information. Classical information theory, actually, the foundation of classical information theory. And first of all, books. These are excellent books. This is an amazing book on classical information theory. It has everything, literally everything. I mean, detailed proof of all the things that I will say here, you can find here in this book. This is a very nice book that contains classical and quantum information theory, and this is the first version of this guy here. That's free to download from Archive, which is amazing. It's an amazing book, this guy, Mark White. And this is a short, nice book on quantum information also. I'm seeing that you're copying this thing. You actually don't need it. I will add the slides here. So the first thing was the B. I mean, one of the basic contributions from Shannon is the notion of B. I think that everybody thinks that bit is so old that Shannon didn't do this, but he did. I mean, usually we have this, we're talking about in 1948. So we had the notion of a bit, which is called physical bit. Physical bit is related with something that happens. I mean, a current, a light here, or anything like this that we can actually see things in one state or the other. This is the physical state of the bit. I mean, like a coin. Shannon introduced the mathematical or logical notion of it. And that's an important thing in information theory. Which means that we are, I mean, how surprised we are when the physical bit is realized. I mean, how much information we learn from these things. This is measured in these sort of bits. So that's the important notion that Shannon introduced, the notion of mathematical or logical bit. This allows me to actually define the measure of information. How much time do I have?
An hour and change, whatever you.
Okay, because you see. Okay. So the first thing, every physical system, we are going now to define what we mean by information, how do we measure information, and then we state the theorem question and prove the theorem. That's the key. We started all of these things we call it information science today. So the first thing is every physical system can be described by what we call a random variable. Random variable is just a thing that we have a set here, this curly x, is a set of everything that can happen. For instance, if you have a coin, then this set is just two things that happen. And this is the probability distribution associated with every one of these possible values. So every system, every physical system in nature we can describe it like this, even the deterministic one. The difference is that for the deterministic system, one of these guys is 1, and all the rest is 0. You can predict anything with certainty. So, one important thing, we consider this guy a finite, countable set. Of course, information theory you can apply for infinite sets and not countable sets, continuous values. But things are a little bit more difficult there. So we keep all of these things in finite and countable sets. And we call this curly set the alphabet. The alphabet is everything that can happen. Okay? And every time you see these guys, I mean the curly variable inside the bars, this means the size of the section, which is called in mathematics cardinality of the section. So this is important because it defines the dimension of the system we are interested in and how much information we have. So these things are defined. We should define what we mean by information. And every theory starts with postulates. Postulates are things that you cannot prove. I mean, they are just assumed to be true, and that's usually the consequences of this. And the consequences of these postulates are Shannon theory. Okay. First of all, the information must depend on the probability of every event to occur. Why this? Well, because we don't want a theory that depends on the physical content of every system. We want a general theory that describes information in general. So the most general thing we have for a physical system is the probability. So it must be a function only of this guy. It must be continuous. Please, if you have a question, just raise your hand. It must be continuous. Why? Because if I change just a little bit the probability of an event to occur, this cannot change too much the information that I get. So it must be a continuous function. That's the intuitive idea of continuous function. And it must be additive for independent events. I mean, if two independent events happen, the information that I get from both of them should be the sum of individual. So these are basic postulates and very well motivated. And what happens is that there is only one function that fulfills these three guys. especially because of these last guys extremely restricted. And this is the logarithm. That's the only function that fulfills this guy. That is why. This is the information that depends on the probability of the event to occur, and we are assuming that you have S independent occurrences of the same event. So I just throw a dice or a coin S times independently. So the information must satisfy this state. This is the joint information of having one occurrence in S minus one occurrence, and then we use the additivity postulate that says this. And then we do the same thing, use the additivity postulate again, and keep going, and then you have that this guy is equal to this guy for S being integer. No. Well, but this implies that this guy, T is an integer also. That this guy is equal to this guy because this guy is 1. But using this guy here, we can put this T here. And then we end up with this for integer T. And then this relation must hold for any rational number. So, probability can be written like this. Let me just validate. And also, any real number can be arbitrarily approximated by a rational number. This is a property of the set of real numbers. So, we can write this equation here. And this is valid arbitrarily well. This guy is, I don't know how do you know about, how much you know about entropy in thermodynamics, for instance. Entropy in thermodynamics is defined up to a conformal transformation. So you can multiply the entropy by any number and add up any number, and this will be the same entropy of the same system. So Shannon entropy happens to be the same thing. Every entropy actually happens to be the same thing. Defined up to a multiplication constant. There is no way to do different. This just fix the units we are measuring information. This happens if you change the basis of this log here, because the results that you just showed here, this should hold for any base for the log. It's just a multiplication factor, so it doesn't matter. So we choose this guy equal to minus 1. 1 because it's just a constant 1, and minus because this guy here is negative. And information should be positive, so we choose a minus, put a minus in front of this, so information is positive. It can be negative, but it's more intuitive as positive. So we just choose this, and this is the measure of information defined by Shannon. This is how much we learn when this event X happens. This is the meaning of this guy here. But we are not actually well interested in this thing. We are interested in the information of the entire system and not a single event. So how do we know? The entire system is properly by this random variable X. We just take the average information. This is the usual way we did. Did I do something?
No, it's the projector.
Okay. So this is the way we compute expectation values in statistics. We just average over all the results, and we have what is called additional entropy, which is denoted by this age here, and this is the information contained on the source. I mean, it's how much information we have from the system when we measure the system. One important thing here is that this is highly dependent on the basis, which means that which question we are asking to the system. Because if we change the questions, we change this guy here. And we change the probabilities, and we change this guy. This doesn't happen for normal entropy, because for normal entropy is invariant under unitary transformation, so it's invariant under base. So it doesn't matter what question you do to the quantum system, you always have the same amount of information. In classical physics, this is different. This is highly dependent on the basis, which makes sense. Because I cannot learn if I don't know what kind of questions I ask to this. These are some important, very important properties of this line. Extremely important. Actually, that we use through the proofs of these things. First of all, it's positive. This is easy to see because it's the expectation value of positive quantity. So it must be positive. This property here is extremely important because area of factors is concave, which means that if I mix two things, uncertainty should decrease. Okay? Okay, and this is one of the properties that we will use. It doesn't matter the value of things. The only thing that matters is the probability. So this causes this guy to be invariant under relabeling of the alphabet. If I change the names of the alphabet cyclically, it doesn't matter. The entropy doesn't change. Because I don't care about the values, I only care about the probabilities. And this thing here is easy to see. I mean, this guy is positive, but it could be bounded for any value, but it's zero. And this is okay because if I have a deterministic system, then if I measure the system, I learn nothing. And if I have a coin that always gives us tails, and I throw the coin and gives me tail, I learn nothing from this. So the entropy should be zero. I have no certainty on this thing. This upper bound here can be proved by using, when you compute the variation of this guy, using, for instance, legendary multipliers, Lagrange multipliers. You can prove that this guy has a maximum value, which is this guy here, and this is which when we have a uniform probability solution, which makes sense because if the probability is uniform, I know absolutely nothing about the system. So when I measure the system, again, I mean, the most information I can get. So these guys are intuitive. And these are, there are many other properties, but these are the most important one for what comes next.
Lucas, you mentioned that you can also do the same definitions for a continuous variable. But I guess all these properties are valid, except that you could now have a negative value. I mean, you have like a differential entropy or whatever, I think.
That's delicate because what Steve is saying that I can do the same thing, but instead of the sum here, we have an integral. So this is always defined, but this is now continuous. Log or log. Log is always taken to base 2. Every time I write log is base 2. Yeah, so information is being measured in bits. Log of bits. The problem is that it can be negative. This can be negative. So what do? Probability is always a conditional probability. You never define probability. You define probability with respect to something, and then you define a reference probability here that turns this thing always positive. That's the point. When I have this guy continuous.
But other than that, all the other properties.
All the other properties hold. Yeah, of course. Of course.
This probability.
This is infinite.
Mm-hmm.
This is infinite.
This case mean the conditional probability.
Yeah, conditional probability. The only thing that I have in nature is conditional probability. I never have just probability. I have probability with respect to something. And when we go to continuous system, we see this clear because, or we do this, or this guy makes no sense. So we need to define a reference probability. Okay. Okay. Any more question? So, theory of communication. Why communication? Because this is what Shannon did. Today, when we talk about information science, we mean a bunch of things that are not contained in this thing. Of course, a consequence of this thing, but are not contained in the original Shannon's work and not contained in the quantum Shannon theory. So this is, we call it communication theory, because Shannon was an engineer, and he was worried about two things. Given amount of information, but how much can I comprise this information? And why this is important? Because I want to send information to any channel. I mean, through electromagnetic waves, as we do with radios, for instance. And and this is expensive. I need to invest energy to create the channel and to send information for the channel. So I want to compress information in order to use less time of the channel and to save energy. This is important. And he was an engineer. This was his job. So what's the maximum rate that I can compress information reliably? Of course, I can compress information to zero, but this is not reliably. Reliably here means that I can decode the information. That's the meaning of reliable. And the answer to this question is entropy. That's the first coding theorem. So this gives you an operational interpretation of Shannon entropy. And of course, the other question is how much information can I transmit over a noisy channel? Because, every channel in nature is noise. Steve knows this very, very well. If I'm talking to you here, you can listen, but if I have an airplane here, you cannot listen to me because there's noise. So how much information can I send over a noisy channel? That's the second channel coding theorem, and the answer is a thing that's called information capacity of the channel. So these two guys, but the two questions were answered in this paper, 1948, by Shannon, and this is information theory was born here. And in 1948, nobody in the world thought that this would be possible. Nobody thought this. So it was entirely surprised to the world when Shannon said, look, it's possible to do this. Let us see how this goes with the first coding theorem. An example of data compression. What do we mean by data compression? Our two guys, Alice and Bob, that everybody knows here, who are these guys, are the same guys that went to the quantum world after this, but they was born Clase. They have an information source that's characterized by this random variable, and this is the alphabet, just for letters. And this is the given probability distribution, okay, for these guys. So this is characterized our system. It doesn't matter what the system is. One thing, the channel takes bits as input. Of course, the physical channel will take, like the radio will take modulations in amplitude or modulations in frequency, but it is still translated to bits to go to the mathematical theory. So we always talk about bits as input to the channels. So we need a code that translates any information that we have into code words, which are these guys. These code words are the things that we can put as input to the channel. In this case, bits. So let us suppose that we choose this code. One important thing of this code is not to be reliable, which means that for every sequence of letters drawn from this probability distribution, according to this probability distribution, it's possible to uniquely decodify the sequence. Otherwise, it makes no sense. So this guy does this. So this introduces the code word and the letter. How we can characterize the code? By the expected length. Expected length of the channel, in this case, it gives us 2. Which means that on average, Alice has to send 2 bits per letter. She has to use twice the channel per letter. Okay? We can do better. Yes, we can. Because this probability distribution It's not uniform. We are using too much times the channel here for a highly improbable bit. So we can use this thing. Let us choose this guy. No. There are 3 bits for this guy, 3 bits for this guy, but they occur with less probability than the rest. And just 1 bit for the highest, for the one with highest probability. That's a clever thing. And we compute, when we compute the length, is 7/4, which means that's smaller than 2. And if you compute the interchannel entropy of this guy, it gives the same number. So this is not a coincidence. What happens here is that this is the optimal code for this guy. Because Shannon, the first Shannon coding theorem says that there is a code that you can compress information at this rate here, which is exactly the entropy. That you cannot do better than this. I mean, there is no way to do better than this.
Lucas, could you go back a slide? So you mentioned that you should be able to know each letter, when a symbol is sent, right? So in the first code, there were always 2 bits, so I just always look at the 2 bits and I have A, B, C, D, and so on. Here I have sometime.
No, not the 2 bits, no, because you send a bunch of letters.
Sure, but I mean, if I'm looking at the, suppose, so I mean, it was clear in the first one, because you always had 2 uses of the channel associated to a letter,
Yeah.
A, B, C, or D. So I know, so I just look at 2 uses of the channel, and I see what are the values, 0, 1, 1, 0, so on, so I can always decode A, B, C, D. But here, sometimes I use the channel once, sometimes I use the channel 3 times, sometimes I use the channel twice. So how do I know how to group all that together?
Because let us suppose that I want to send you 10 letters.
Mhm.
And then we have A,
Excuse me, can you write larger, please?
Okay.
Thank you very much.
A, like this?
See?
Okay. B is less probable, then we have, I don't know, C, A again, and then D is one, over A. I want to send you this guy. What you get in the output of the channel is a sequence of bits, which is 0, which is 0, which is 1, 0, and then we have a C that's 1, 0, 1, 0, and then we have an A again, that's 0, and then we have the D that's 1, 1, 1. There is a neat way to decode this guy into this guy. So you just, of course, Bob knows the code.
Sure, yeah.
So that isn't 0, 0. So there isn't a symbol that's 0, 0. So this must be A.
A is the only symbol that, say, starts with 0.
Exactly. And this is decodable. It doesn't matter the sequence. It's always decodable in Euro. And that's what I meant by reliable. Yeah, because I mean the output of the channel is always this. So that's the meaning of the channel first thing that you know. Okay, how to prove this thing? That's what the breakthrough idea from Shannon. That's instead of studying each one of those symbols, he thought, no, let the source emit a bunch of symbols and codify everything at once. Different from what we did here. What we write a code word for every letter. We just make a code to write the code word for this guy. An entire sequence of letters. I mean, a book, an entire book. And I codify entire book. And it goes to infinite in that. That's the only way for us to that channel found it to solve this problem. If you treat each bit individually, then you cannot do this. It's impossible. So Shannon thought, let us associate a bunch of things. So that's the notation. This guy here is the first realization of this random variable. x with an index I, and this guy here is a random variable that contains all of the sequences. So it's a random variable that each sequence is a random variable with a bunch of symbols, and we have a bunch of sequences. And the limit, the symptotic limit is going to be taking for this guy going to infinite and an infinite amount of sequences. This was the idea for Shell. And this allows us to prove the theorems because it's much easier to deal with average than with individual events. So, and this thing allowed him to define this guy here, typical sequences. And today, typicality is a very, very, very important thing that we have. For instance, if I have the space of all quantum states of a given system, many-body system, if I pick up randomly one of the states, it will be typically entangled. This is typicality in quantum mechanics. So, and this explains the fundamental postulate of classical, well, statistical physics, that says that a local part of the system behaves as if the entire system is in microeconomic constant. So, we are going to show the typicality in classical physics. And that's what Shannon did. We have a sequence, a huge sequence of symbols, realizations of random variables here, the same random variable. And then we encode the entire sequence, use the channel less times than we have here, fewer lines than we have here. So this is compactifying information, I'm compressing information. This means that identity channel, it does simply nothing. And then Bob decodes the guy and reads the sequence. That's it. And these guys go to infinite. The question is how many lines should I have? Because this is how many times should I use the channel in order to send the sequence that way. Let's do this thing. And here is the second hypothesis. Without this hypothesis, it's impossible to prove anything. So this lies in the basis of information theory, and this is important to you to understand this thing because if your system doesn't fulfill this guy, then you cannot apply information theory. You must take into account correlations between different realizations. So you must be careful when applying these things because this hypothesis lies in the very basis of everything. And this means that every use of the channel is dependent on any other use. And every way I throw a symbol here, I draw a symbol here, it will be drawn with the same probability. That's what is meant by independently and identically distributed system. Okay? So this means that we can simplify this guy because we wanted the probability of this sequence to happen. This is simply the joint probability of every symbol to happen. And then we apply independence. Independence means this. So we can simply multiply the probabilities of individual things to happen. And then we apply the property that they have the same probability distribution. All of them, the x. And then we end up with this thing. So that's much easier to compute than this. But it can do better. We just label the letters in this alphabetically X here, like AI, and I goes to from 1 to the cardinality of the set. And then we mean this guy is the number of times the letter AI appears in the sequence next to it. For instance, I can ask you how much times the 0 appears in the sequence. So this guy is just the number. So we can rewrite this thing here like this. And this is much easier to compute because this guy is much smaller than this guy. So smaller numbers of multiplications, much easier to compute this guy here. Everything's okay? Huh? Okay. Okay. Then we want the probability of this guy. Because probability of the source from a huge sequence. That's governed by these random variable. And that's what we want to investigate. And then we define the sample average of this guy. The sample average is just the information of this guy divided by the total length of the sequence of the set. This is a definition. This is called the sample entropy of the random sequence. Let us investigate this guy. So defining this guy the same way we just did, but now for the entire sequence, and not for a specific sequence, but the entire one. Use again the same hypothesis. This will be used everywhere. And then we can do the same thing and write the thing like this. So this is just, basically math. But for those who got a course on experimental physics, what you do in the lab, in the experimental physics 1 or 2, is to count the distance. This is exactly this. And you call this thing probability. But that's the definition of probability. When this guy goes to infinite, this converts to the probability, which means that when I take the limit of this guy here, that's the information that I'm using, this random variable. I have this guy here. This guy goes to the probability, and this guy is just the entropy of the source, because they are identically distributed. So the sequence of every random variable x, I is px, is the same thing. So it's highly likely that the random sequences satisfy this thing here. So what does this mean? This means that the information, the sample entropy of the random sequence, the probability of this guy being the entropy of the source goes to 1, because these guys are arbitrary. This is very important, and this means that if I have a source of information that's emitting a bunch of symbols, and I count the sample entropy of this guy, it will fast converge to the entropy of the source. Well, not that fast. I did the calculations of this guy here for a coin with not equal probability, and this guy approaches 0 when I have 10 to 6, and this n here goes to 10 to 6 or bigger. Then you have convergence of this guy. So this must be huge. So this allows channel to split the entire set of sequences into 2. One is the typical sequence, which defines just all sequences that fulfill this thing. So its sample entropy of that sequence is equal to the entropy of the source. We call it this a typical sequence. And the typical set is the set of all of these things, all of these sequences. And you have the rest. So you have the entire sequence that you have every sequence there, and you have inside of this you have a typical set, which contains this sequence, just this one. And then this is the typical set, and the definition of the typical set is the set of all sequences whose sample entropy approaches the channel entropy of the source. Arbitrarily well. Okay? Then channels idea. Just code this guy. Throw away the rest. If the source emits a sequence that's not typical, it's simply throw away, isn't it? Why this works? Why this is a good thing to do? Because of this property. That's fundamental. This is a fundamental property of channel because it says that the typical set contains almost all the probability, which means that it's highly likely that the information source will emit a sequence inside the typical set. So this makes the probability of error goes to 0. The typical set is exponentially smaller, which means that I have to code an exponentially smaller number of sequences. This is information compression. This is data compression. I'm just throwing away that sequence that has no probability to occur. So I'm not compressing information, just throw away the part that's not important. And this is called information compression because of this thing here. And each typical sequence has the same probability to happen. So this set of properties here of this guy here is known as asymptotic partition property. This makes information theory asymptotic. So we cannot do information theory for a few occurrences. The Shannon theorem doesn't hold for this guy. We needed to take the asymptotic limit. So of course, when we're doing experiments, it's impossible to take the asymptotic limit, but we can get close. This asymptotic for a physicist is very different from a mathematician. It's like infinite. 1 meter can be infinite for a physicist. If you're compared to the size of an electron, it's infinite. So
It has to be infinite for a photon.
yeah, exactly. So, but this when you apply information theory in anything, you must take into account that these properties should hold. Otherwise, you are applying the theory incorrectly. Okay. Let us see. How this is going. In order to prove the first property, you need to prove this guy. The probability of the sequence to the probability of the sequence to be in the typical set.
Yeah, when you said that we discard all the sets that are not part of the typical set,
Yeah.
you refer, for example, like a code like was 0, 1, 0, 1, 0, 1, that is not part of the
No. The typical set is defined in terms of the sample entropy. And what I mean by this property, the asymptotic partition property is just this. It doesn't matter which sequences are typical or not. You need to check these for every experiment. You have, this is the total set, the curve X. So the size of this guy is 2n log this guy. That's the size of the entire set. And then you have the typical set here. The typical set, so if this guy is not uniform, this guy is exponentially smaller than this guy. What Shannon realizes that the sequence usually, the source usually with high probability emits the sequence that lies here.
Okay.
And then he said, oh, just codify this guy and throw away the rest. But which sequences are typical or not, Bob needs to check. In how he checks, computing the sample entropy. If it's not typical, then I simply declare error, and that's okay. The question is, what should I do to make the probability of this error to occur goes to 0? So this is what's being proven here. I want the probability of the source to emit a sequence that is inside the typical set here should go to 1. And this is what we want. How I make this epsilon goes to 0. Then I make sure that the error here goes to 0. And this is actually, this is a thing you call it the law of large numbers. It's just law of large numbers applied to this guy. This thing is amazing. Shannon just realized it is. So
that means, so I'm thinking about sending messages in, say, a language, like the English language. And so, some letters in the English language appear much more frequently than others.
Exactly.
A and E are much more common than, say, Z.
Exactly.
So if my N is large enough, any message I send should have a certain number of E's and A's and so on as the entire language. That's more or less what you're saying?
Not the entire language. I mean, the size of the set is the English in English. You have 27 letters in English? Yeah, something like this. I mean, 26, 27 letters, and you have a probability distribution. I mean, if you have a library, you count the number of A's that appear in all the books in the library, and the numbers of B's and the number of C's, and then you have a probability distribution of this guy. So a library is big enough for this. And then you pick up a random thing, a random message.
Random book.
Yeah, the random book would be the entire. And then you qualify just this guy.
And
That's the idea of qualifying this thing. But you see, if the probability is equal to everybody, every letter, then
yeah, sure. But like a non-typical, say something that's in a non-typical set would be, say, if half of the letters in my sample are all Z, which is like,
yeah,
yeah.
this one.
So
Yeah.
I don't even have to worry about coding that.
Yeah, you don't need that. Yeah, exactly. This is an error. So we define the expectation value of the random variable like this. I mean, just the mean of the random variable. And then we use the law of large numbers. That's just the statement of the law of large numbers, which means that for all epsilon and deltas greater than 0, I mean any one, that is this number here, so that for any n bigger than this guy, the probability of this sample average to be close, delta closer to the expectation value of the random variable is close to 1. Okay, that's the law of large numbers. This is exactly when n goes to infinity. This is a mathematical result that Shannon realizes that, oh, I can apply this thing if I consider that my random variable is the information of the sequence. So I can do this thing. Because of this guy here that we saw just a few slides ago, and this holds because of this hypothesis. Otherwise, it doesn't hold. So, if I complete the expectation value of this guy, it's just the Shannon entropy, because it's the definition of Shannon entropy, actually. That we denoted by mu in the other slide. Therefore, if you apply the laws of large number just when you plug in the variables here in this equation, we have this guy. But this is exactly the definition of the typical set. It's exactly the same thing. So it's highly likely that the sequence will be typical. So the typical set contains all the probability. And I can do this as close as I want to 1. So Shannon proved that if n is big enough, every sequence that will be emitted by the source will be here. Which means that the probability of error is small. That was the clever breakthrough that Shannon had to solve the problem. And it makes sense actually, because this is actually true. The third property of this asymptotic equipartition property, we have to show that the entropy is delta close to the entropy of the source based on the definition of the entropy. Well, sample entropy, we have this thing, because sample entropy is defined in terms of the logarithm, so the exponentials. So this is just taking the definition of this guy, of the sample entropy of this guy, and this implies this directly. This directly implies this. But delta is very close to 0, symmetrically small, which means that this guy is uniformly distributed. So the probability of each sequence in this set to be emitted by the source is the same. And it becomes essentially the same when in the asymptotic limit when this guy goes to 0. So the probability is uniform. That's the third property. Now we use this third property to prove the second one, which is a partition. But this actually is a partition. This is because the name is partition, because the probability is distributed over the entire side equally. Asymptotic because we need to take the limit of n goes to infinity. So we need to show that this guy is exponentially small, because if this guy is equal to this guy, then you're not compressing anything. This is easy to do. I mean, like this is an identity, and this guy is always true because this guy is always smaller than this guy. So this guy is always true. These guys are just the property here. But this guy is a constant. So it gets out of the summation, and the summation is the cardinality of the set. So the cardinality of the set is given by this guy, which will be compared with this guy here. So as long as remember that this guy is equal to this guy here for a uniform probability distribution. So when the probability distribution is uniform, then this guy is equal to this guy, and you cannot compress information. That's totally random. You simply cannot compress this thing. It's possible to bound from below also this guy, and but we don't care about this thing. No. But is it now clear why these things work? I mean, the idea behind these things. All these calculations are presented in those books that I showed there before, but they are the idea is important.
Something I forgot to say in the beginning, I'm assuming we can ask questions in Spanish,
Of course.
English, or
Of course.
Portuguese, correct? So-
Of course. Of course.
So, we can-
Okay, we have introduced this typical set and the property that A and B, that is extremely important. So we need to prove the rate now. That the rate of compression is equal to the entropy. That's missing here. So we need to assume a code. A code is the length of the sequences, are the rate that which we're compressing. Epsilon is the area that we are. Okay. And we have the encoding and decoding schemes like this. I just go from this set, one encoding to 0, 1 at this range here. So I have a length of n sequences. Do you remember my draw in my picture a few slides ago? We have n entrances and n times r outputs. So this is the number of times I have to use the channel. So I needed to find this guy. Who is this guy? And the decoding should be the same, but the opposite is the inverse. I should be able to apply my code in such a way that to get the same sequence without losing information. The probability of error is just this thing. I mean, the encoding and then composed with decoding. The probability of this guy to be different from the input sequence must be smaller or equal to epsilon. Okay, this is the definition of probability of error. So when this epsilon goes to 0, I have a perfect. So, and the rate is defined as just the number of channel uses by the length of the sequence. I mean, this is just a definition of the rate. So, I only qualify these guys here, and the rest I simply throw away. That's channels breakthrough idea. The code will always work because of the AP property. So we know that this thing works. And due to exponentially small cardinality, we have that this guy is equal to this guy. If I remember the size, when we bounded the size, because this property here bounded the size of the typical set by this guy here. And then we just compute the rate is equal to this guy. When this guy goes to 0, it's exactly this guy. So the rate that I can compress information is the channel entropy. So this gives an operational interpretation of the channel entropy. And this is just the way we do. I mean, we pick up a function that transmits this guy, and this guy is an error. And do it to this property, the probability of this error to occur equals to 0, because the error only occurs when the source is sequence outside of this. This doesn't work when I have this thing. Uniform probabilities. There is no way to compress absolutely random things. Questions? So, how much time do I have, Chief? My watch is
Say 20, 30 minutes.
30 minutes, okay. Okay, let us start a little bit. Of course, if you have questions, you can also not comment. Some things that we need to define. These will go faster because, I mean, a bunch of things we already presented here. This is just a joint entropy, the joint of two random variables, the information that I have when I learn the realization of two random variables. It doesn't matter if they are correlated or not. I mean, simply doesn't matter. So it's a joint probability, and this is the conditional probability. It's extremely important. So it's by how much my information, my entropy about epsilon decreases when I learn the value of the random variable x. So to learn this thing, I needed to measure the thing. This is completely different in quantum mechanics, because to measure the quantum system, I changed the system. So this guy is not well defined in quantum mechanics, because measurement that is really different from classical physics, but here it is. So this guy is perfectly defined. It's positive. It's always beautiful. And this is the mutual information, which basically is a way to tell apart this guy from this guy. But this guy is the marginal probability of x and the marginal probability of y, which means that I'm trying to tell apart the joint probability from the product of the probability, which means that I'm measuring correlations. Because this guy is equal to this guy if they are independent. If they are not independent, this guy will not be equal to this guy, and there will be correlations. So that's the meaning of this guy. This measure a measure for all the correlations contained in this. This holds also in quantum mechanics. And then the mutual information can be written like this in terms of the individual variables and the joint entropy.
Just show that I just used the property of the logarithm, correct?
Oh yeah. Yes. And a very important quantity is this guy here. Extremely important. Physics actually and information theory. For instance, I can prove the second law of thermodynamics by the positivity of this guy. From the positivity of this guy. This means, suppose that I have a system that has a probability distribution that is P, but I think that the probability distribution is Q. But how much I'm mistaken? This is the thing. So this, if I have a coin, a fair coin, and a coin that's not fair, and I give you one of the coins, this guy says how hard it is for you by throwing the coin to tell apart the two coins. This is not symmetric, because if I give you the fair coin, then you throw the coin, you can have tails. But if I give you a completely unfair coin, that always gives you tail. You can throw and always tails. This is a possible result for a fair coin also. But if the fair coin gives you heads, then you know with a single measurement that you have the fair coin. So that's why this guy is not symmetric, and that's why this guy is infinite. The example that said just give you this is infinite, and that's why this thing is called a divergence in literature. But it's always positive and zero only when this happens. Okay. Now we can study channel second theorem. Second theorem is just, let's just suppose that Alice and Bob now are connected by a not ideal channel, which means noisy channel. There is some kind of noise in the middle that corrupted the data. We use a discrete channel that holds for continuity as whole, but it's much more delicate because of these issues. So I describe the channel mathematically as the X, which is a random variable input in the channel, and another random variable, which is Y, that's output of the channel. What I want is that this guy is equal to this guy. This is perfect communication. So I described the channel mathematically by a probability, by conditional probability. By how much this guy, by learning these guys, the output, how much can I say about the input of the channel? So if they are totally correlated, then I can say everything, and the communication is perfect. So this is a mathematical model of the channel. Channel capacity. Channel capacity, I wanted this guy to be maximum. Why? Why? Because if this guy is maximally correlated, X and Y are maximally correlated, then for every output, I can tell the input. So this, I want the maximum correlation between the input and output. That's why the capacity of the channel is defined like this. So let's think about the channel, bit flip channel. A bit flip channel, it just flips the input bit with probability P and leaves it unchanged with probability 1 minus P. Okay? So if I have a P going to 0, then I can communicate over this channel. If a P is big, then I cannot communicate over this channel. This is what we call noisy channel. But I can use a code like I qualify every 0, which is the input of the channel, into 3 zeros. So I use the channel 3 times. Mm-hmm. And Bob gets there. If he sees 3 zeros, then he assumes that there is a 0. If he sees 2 zeros, then he assumes that there is a 0. So majority function, just like this. It's the easy error correction code. But Alice must use, to send one bit, must use 3 times. The probability for this to work, the probability of error should be smaller than P. That's the probability of error. It's easy to compute this guy because it's the probability of 3 flips, and this is 3 times the probability of 2 flips, which leaves Bob with a wrong decodification. And when this is smaller than P, then I have a better code, better way to communicate them just using the code there, the channel. But this only happens when this guy is smaller than what's not good. Well, I can concatenate codes. So I can use 9 times the channel in order to send it a 0. But this is bad because, of course, this decreases the probability of error, but this is bad because in the first coding, we use the rate is 1/3, 1/3. And these guys goes to 1/9. A second concatenation goes to 1/27. So I get the probability of error going to 0, but the rate of communication also vanishes. So I cannot communicate with state. It's impossible. And that's the question that Shannon answered. And everybody in 1948 thought that the answer to this question was no. Shannon said no. The answer is yes, I can do this. I just need to send it below the channel capacity. And the channel capacity is like this. The same thing. Let the source emit a bunch of symbols and then send everybody. Qualify everybody. So you have a messages here, a set of messages that the LC has there, labeling from 1 to m, and big, very, very big number. And the channel is just, characterized by this longitudinal probability distribution, and we have the same notation as before. We have the set of sequences in the input, the set of sequences in the output of the channel, and this is one sequence, this is another sequence, and everything here is identical, independent and identically distributed uses of the channel. And so this hypothesis is everywhere there. This allows us to write the conditional probabilities like this, the same way we did before, usual probability. And the range of this guy is defined in the single way, the number of messages bits divided by the number of uses of the channel, which is n actually. And then we have log m, which is the number of message bits that we have. How many bits we are sending per use of the channel. That's the range. So giving a code is just, it's translated the alphabet to the code words that will be put into the channel. The average probability of error in this guy is just a definition of probability. This is the probability of error associated with the message n. With the code C. Sorry? No. So, this is a theorem that's shown a probability of error, the average probability of error, if it's smaller than certain number epsilon, then it's possible to bound the probability of error of every message by this guy. Here is at least, as a T is missing here, half of the messages in here.
The channel is noisy.
Yeah, the channel is noisy, yeah. So, channel theorem says that there is a code that achieves this probability of error, it goes to C. This, at least for half of the messages, will be important later. But Shannon knew this. So, to prove this thing, Shannon used the laws of large numbers. That's why he needs a huge sequences. Otherwise, he cannot apply this thing. And also probability theory. Because if I have just a small number of occurrences, I cannot define probabilities. That's not possible. There is no way. Typical sequences and typical sets, the same thing. And he also introduced a new randomness in the thing. He said, no, let Alice to choose the codes random. This apparently makes no sense because what does this mean? Alice choose the code randomly, how Bob is going to decode this thing. The problem is that if I bound averages, I bound the probabilities. So he thought, let the code be chosen randomly, then I stood the average of the probabilities with respect to the code, and then I bounded the error of each code. That was his second breakthrough. Because nobody will talk about this. The code is the code, it's not random, it's just, we cannot communicate with different codes. If everybody here speaks a different language, then it makes no sense. Random makes no sense, but it makes sense. That was clever idea by Shannon. The proof of this theorem is much more complicated than the other one. So I'm not gonna give you the entire proof here because it's spread over several chapters of every book because you need a bunch of things. But the idea is simple. So the coding words are chosen in a random way according to a given probability distribution of the source. And then I have the same thing, each letter, a coding word of this guy selected according to probability distribution of this guy. And so the coding word itself becomes a random one for each message n. So given that this choice is identically independently distributed, as always, we can simply do the same thing as we did before and write this thing. So as always. The probability distribution does not depend explicitly on n, because it depends on this guy here and not explicitly on the message, because the message doesn't matter. I mean, it doesn't matter. It doesn't matter what Alice is saying. I just want to understand if Alice can send something or not. So the message itself doesn't. It is not important. And then the probability of a given code is this guy. It's just a probability because of this hypothesis here. So I can write this equation here. This simplifies a lot. And then that's why he chooses the codes, because he wants to understand the average probability of the average probability. Because it's easier to do this. And this is easy to compute. Since this guy does not depend on the message itself, I can simply choose one of these. I can simply choose any message from 1 to n. It doesn't matter, it's all the same. And then Shannon, with this, Shannon proceeded by putting an upper bound of this guy. So he has an upper bound of average probability of this guy. With this, based on the theorem that you just showed, he was able to put an upper bound of this guy. This is the thing that he wants. And this throws away the randomness of the code. Because this is a single code. I mean, there is a single code, a specific code, for which, given this bound here, you have this guy. So the randomness of the code introduced it just to be able to do this computation. And if you pick up Mark's Wilde book, he does this, I think that chapter 18 or something like this, he does this calculation. It's a little bit complicated, but he does everything. So he proved that if this boundary was computed by Shannon, and then this implies this bound.
Find that code, that optimistic code, is a polynomial problem?
This is a question that I will mention at the end of the thing, because I mean it's always this way information theory. Look, that is this thing, but how do I compute this thing? Well, this is not. It's always like this. This is another problem. I just want to understand if this is possible. It's possible, yeah. And it's always like this. To find the code is different. And usually it's not easy to find the optimal code. It's extremely hard, actually. I mean, to compute the channel, the capacity of the channel is an extremely hard problem. Give a channel, compute the capacity is almost impossible. Even numerical is hard for them. And there are more problems. If I give you two channels, then the capacity of these two channels together will be the sum of the individual capacities. Classically, yes. Quantum mechanically, no, then we don't know why. This is the additivity of the channel problem. It's one of the most important problems in this field. I remember that a guy called Martin Hastings published in Nature Physics just because he found a complex example of additivity. Yeah, he was able to compute the thing. It's extremely difficult to compute this thing. To find the code is incredibly hard. Usually you get a code, and then that's it.
The typical set is in base of the code of the set that I want to code.
No. This is just the typical sets are just the sets with respect to the messages. The code doesn't matter because the channel just introduces the randomness in the code and then throw away. It's just it's a mathematical tool for computing these guys. So, but remember that we have just this bound holds. I mean, this bound implies this bound for half of the sentence, not for an entire sample. So we thought, oh, I simply throw away the half with the worst probability. And so you are throwing too much away. But the problem is that the number of messages decreases from this guy to this guy. But which implies that the range goes from this guy to this guy. But when n goes to infinity, this guy doesn't matter. This guy doesn't matter. And in the asymptotic limit, it's possible to prove that there is a code where the maximum probability of error is this guy. And that was the first part of proving the second coding theorem. And I'm just writing the set, the number of messages decrease. We are almost finishing, but we want one thing, to keep the rate constant and take it as a total limit. And we have the maximum allowed rate while vanishing small probability. Okay? To do this, we need to determine the number of distinguishable messages Alice has in Chile. So how can we build the code? That's a question that is going in the direction that you just mentioned. I mean, it's not completely accurate. Our rule is to build the code. You cannot give any code. And the way we build the code is this way. We give it the code word and the output code word, and these are related by conditional probabilities. The problem is that if Bob gets this guy, how can determine X because of the original message? That's the thing that Bob wants to do. And the problem is that for conditional probabilities also holds the typical set assumption. I mean, there is a conditional typical set. And this is another thing that generalizes. For every message here, if the channel here is identity noiseless, then there will be just one single point. That will be in this setting. But the channel is not noiseless, it's noisy. So we have this guy here will be mapped into a set here. And it's possible to prove that in the asymptotic limit, the size of the set is given by this guy, where this guy is the conditional probability. Given X, we have the typical set UI. And this guy here is the total set. Okay? So the way to do this is easy. I mean, first, you have to prove asymptotic partition property. It's basically the same thing that we showed, but a little bit more complicated because you are using conditional probabilities and things like this. But it's possible to prove that it has almost all the probability of the same thing. It has unit probability, the conditional set. Its size is approximately this thing with small cardinality also, unless that is exact. Uniform probability for the conditional sequences. Every sequence in the conditional typical set has the same probability. So it's the same thing. How to build the code. Alice generates these guys' messages according to PX. It's the message set of messages that she wants to communicate to Bob. Bob doesn't know these things. So he assumed that the output is generated a sequence Y, which is given by this probability distribution. Because he doesn't know the messages. Bob, once he gets a message, Bob verifies if this guy belongs to the typical section of the variable Y, which is this typical section, not the conditional one, just this one. By computing the sample entropy, he can do this. So the size of this set is this guy. If it's there, then now he needs to understand it to each conditional typical set, this guy belongs. because it lies in the typical set, so the communication works. But in which conditional typical set this guy belongs? Because I want to know the message that was sent. So they must structure the code like this. They must divide the typical set here. This is, let us change the letters. Why? They must divide this guy into m subsets. Or, let me do this time. This is the typical set of the input with big M sequences. And this is the typical set of model, this one. So they must divide this guy into m subsets that do not overlap. Because if they don't overlap, then I can tell once I determine the sequence is here, I know that the input was this one. So that's the way they should structure the sets. And so the number of this guy is just this guy, and the number of messages must be bounded like this. Otherwise, there will be overlapping sets, subsets, and the communication cannot be done. And this is the range. The range here is equal to this guy, but this guy is the mutual information. It's exactly the mutual information. That's why the mutual information is bound. Because if I put more sets here than given by this number here, or more messages, then the conditional typical sets will start overlapping and communication will fail. This is the maximum possible thing that you can do. There's no way to do better than this. And but the picture is this. I mean, this guy should not overlap. And then the range must be smaller than the mutual information. There is no way. And since Alice chose the coding according to this guy, the mutual information is concave, which is a very important property, which means that there is a single probability distribution that maximizes this guy because of concavity of the function. So they just need to choose this probability distribution that maximizes this thing, the code is defined, and they have the channel capacity. That's the maximum possible range that information can be transmitted over the channel. We hardly achieve this in physical systems. Extremely difficult, because we cannot determine this. It's extremely hard. But I mean, in principle, we can do this. We can communicate at finite range without problems. So that's the channel theory, an overview of channel theory. We just given out to look at channel theory, and these two theorems are lies in the basis of all information theory, both classical and quantum. And we have that information can be compressed, but the rate is smaller than the channel entropy. And information can be transmitted as long as we use a range smaller than the channel capacity, which is given by this guy. One thing that we didn't prove was optimality. We proved that this is possible, but that there is a maximal range, but we didn't prove that the code is actually optimal. These are called converse theorems, which is extremely dedicated to prove, and that's why I did it over here. These are complicated, but there is a way to prove the converse way. So this is the optimal thing, and with this I finally finish. Sorry for so much time, and thank you for your attention. Questions or comments? I promise that on Thursday will be more physical things.
Another one. In one moment you said that the entropy of the channel, or maximal capacity of the channel was bounded by the logarithm of the distribution.
The maximum capacity of the channel.
One is like the beginning, like the the entropy is something like goes with the logarithm, right?
Yes.
But we all the time use base 2.
Yes.
We encode the message in, for example, 013 or
Oh, yes. You can use whatever base you want.
the capacity will increase of the message we can send for the channel.
Oh, not really, because I mean, the capacity of the channel is given by this quantity here. It's the unit information. It doesn't matter the bases you are using. And anyway, I can multiply this number by any number that I want, except 0, of course. By any number, and this will be the same thing. The problem is that how do you define communication? You need to define the basis that you are communicating, and then you define these guys. For instance, you can communicate using electromagnetic waves, which will not be 0 or 1. A radio communicates by modulating amplitude over time. So these are continuous variables, and these things hold. All that matters is that the rate is the unit information. And the maximum unit information. You can't communicate with this. It doesn't matter the channel, it doesn't matter the basis, it doesn't matter the physical means that you're using. I mean, this is amazing theory. I mean, it's amazing that somebody could talk about this thing and actually did this. Shannon's paper is brilliant.
I have a question. So when we talk about optical channel capacity in optical fiber, we spoke about this result specific.
This?
This result.
Yeah,
Is this also
this also holds. This also holds for any channel. But the way you define these things is a little bit complicated because you are treating continuous distributions. So you just to be careful. But the determinant also holds. You cannot do this. This is independent of the channel.
Okay.
I guess it also assumes that the states, how can I say this, the possible messages or what have you at the end in the receiver are orthogonal in the sense that they're distinguishable.
Yeah, they should be distinguishable. Otherwise, it's impossible.
When you go to, like when you talk about rates in like an optical channel, but have say quantum states and you have states that are not orthogonal and so on, then it changes it.
It changes, yeah. If they are not orthogonal, you cannot distinguish these guys, and then you have a different thing. Here we assume that the sequences, the output sequence can be distinguished from each other. Otherwise, you have to use a block and.
Are there any more questions? You can ask in Spanish as well.
Yeah.
No? Okay, well, just before we conclude, as Lucas mentioned, he will be here until next Thursday. So if you have questions or
Welcome, my door.
he will give another class on Thursday. And so, so he's here for questions, discussions, complaints.
Just go ahead.
Okay, well, let's thank Lucas again.
Thank you.